So the next speaker is Dr. Dongjun. He's a professor with Department of Mechanical and Aerospace Engineering at Seoul National University. His research interests include robot mechanics and control, teleoperation system, and robot manipulation. So, Professor Lee, you can start your presentation whenever you are ready.
Okay, great. Okay, so just let me check the time. Okay, I see. Okay, so it's thanks for the invitation for this great workshop. I think that I found the many talk very interesting. So far, I think that there is a kind of more about the control and algorithm and so on and so forth. But my talk is a little bit different in the sense that now it touches the more intuitive and efficient direct interface between this swarm and the human. Particularly, I'm interested in this human-swarm interaction for 3D swarms. So 2D swarm is very easy in some sense to interact with. For example, by just using a tablet, right? However, 3D swarm is kind of difficult to designate some location or manipulate those agents in 3D environments. And so that's something that I think that it defines quite interesting problem. And I wish that some of you also found it interesting and start working on that. So these are my students. So I really don't know much about the details. They all know. I will just give you a kind of a high level talk. So title is a robust hand tracking for 3D human swarm interaction. And HSI is a human swarm interaction. Okay. So I can just move on. So today I will first discuss about the motivations, why hand-based 3D swarm interaction is necessary. And I will also show some preliminary results, very, very preliminary, but I think that's still interesting, done in my lab to you. Then, however, if you try to implement hand tracking for your swarm interaction, you will encounter the problem that there are not many commercial solutions. So I will discuss you about this state of art of these hand tracking technologies. And then I will present and explain our recent results in this direction, which is visual inertial skeletal tracking. Okay, so VIST. Okay, then if time permits, then I will also discuss a little bit about this far future vision about this multi-user 3D human swarm interaction. Okay. Okay, so this is one of the very rare examples of this swarm robotics. Okay, it's a leaderless local interaction, very interesting, looks very nice. And the key idea about this swarm robotics is that by using very simple control, we can have this emergent behavior. Okay, emergent. Emergent means that it is not really well controlled. Okay, and also we all know that it's fairly difficult to prove that if we have a specific applications, and particularly if environment is just like this, then it's a little bit easy. However, if you consider the environments which is non-convex, very, very complicated geometry, it's very, very difficult to prove something. Okay. So then, in order to make a little bit more useful for specific applications, so this is one of the examples I found very interesting. So kind of regulating emergent behavior by using guise or fixture. Okay, later on I will use this terminology, virtual fixture, very often. So you can see that it's just local interaction. However, if we have this kind of a guide, then we can modulate its behavior to our desired behavior. Okay. So then, this is 2D. Okay, this is 2D. Okay, it's kind of easy to realize this kind of applications. For example, by using just tablet. Okay. Okay. So then, 2D human swarm interaction is a little bit easy in my perspective. However, if we extend it to 3D swarms, like a 3D drones, then now things get very, very messy and complicated. And this is the simulation, actually a real-time simulation about this virtual environments with this kind of agents. And then we all know that we use a Reynolds controller or BSX model. So it's all distributed, okay? Then now you can see that it may look okay, but now you can see that already some swarm splits. We all know that we are interested in swarm robotics because we want to use cheap and simple robots, okay? And also we all know that if we work on the control, then it's very easy, particularly if a control has a saturation, control has an uncertainty, sensing is uncertainty. It's very easy to have this kind of disconnection of agents, okay? So, and particularly if environment is simple, it's just void, then it's kind of easy to control this kind of swarm. However, as you can see here, real application requires us to work on environments which is non-convex, complex, and also swarm control and sensings are also imperfect. So swarm can split, okay? So then if we have this kind of split, then what would you do? Okay, what you want to do would be likely that try to modulate or choose, so virtual world we just saw for that example of this ship herding, we may want to use or implement that kind of a 3D virtual world or virtual picture, okay? It sounds easy, however, it's a 3D environment. How will you define this 3D virtual picture in this 3D environment? The easiest one is using keyboard, okay? Just like that, if we have this collaborative robot, it has this tablet, okay? However, can you imagine that which kind of coordinates numbers will be for keyboarding that kind of information, right? It's not really intuitive and it's not really very efficient. Another very, very good way of interfacing is if you buy like Oculus Quest, then they have this kind of controller. Then this controller has this kind of ray, right? And you can also control this environment by using this ray, right? However, now let us just imagine that how to define 3D virtual picture by using just ray. If space is void, it would be kind of doable. However, if we have like a world, another world, however, suppose that we want to define virtual picture somewhere over there, then ray will have this occlusion problem, right? And also in order to define this ray, because now this ray is just one-dimensional information, then we need to have several operations to make this kind of a 3D environment, 3D virtual picture. Okay. So then, for this, essentially what we want is to define 3D virtual picture, okay, and also rotate it, enlarge it, translate it. So actually, it's a manipulation problem, right? And also suppose that we have this kind of outlier. We want to choose them in 3D environments. Again, it's very, very difficult to choose them by using this keyboarding information, right? Keyboard information, coordinates, right? Much easier, just use hand and grab it, okay? And move it, rotating it. So again, this is a manipulation problem. Let us also consider this problem of sensing, okay? So then we all know that so this AI is very powerful. However, what they are doing is that to emulate humans' perception, which is very good to localize and identify important information, right? However, autonomously recognize those kind of information is not so easy, particularly when we consider this swarm robot, which is simple and cheap. Okay? And also, this is an example of this 3D environments. So this is by using this visual inertial SLAM. Okay, and this is actually active sensing problem. So one agent is trying to make a map, and based on that, second agents have the kind of a trajectory optimization to maximize information gathering. Sounds very simple, right? Impossible to run it in real time. Computationally very, very expensive. However, this kind of thing would be not that difficult if human can directly control that, because humans are good at detecting which kind of a scene has more information and so on and so forth, right? So then, in order for this, so then it's also, again, manipulation problem. Choose some specific objects and maybe choose some specific group of agents in 3D environments and maybe move them and align them toward the objects, okay? And also, if you see this kind of information, this kind of map, you will naturally triggered to want to make it some part of that map to be big and rotate to better see what's going on inside there, right? So then again, choose, rotate, enlarge is a manipulation problem. Again, keyboard, brain is a controller using that kind of array information are not really intuitive and also not really efficient. Manipulation, we have this hand, best solution from this evolution, right? So that's why that I argue that we need to use this hand, and using this hand will make swarm control much more efficient and much more intuitive and also much more fun. Okay, so these are again very, very primitive and preliminary implementation done in my lab. So if you see on the left top, then you can see that now manipulating this kind of virtual fixture, right, to split this kind of swarm. Second one is just defining in 3D environments just waypoints, okay, by using this finger, and down right, then it's just drawing a letter, okay, and this is the another example. You can see that it defines this kind of a virtual fixture like a potential field to push those kind of. So if you see a little bit here, oh, not going back. So you see that it's kind of a molding this kind of swarm agents, right? And guiding while avoiding collision by defining this potential field around these obstacles in a very, very intuitive way, okay? So this is another example. It's just a snapshot, so we can just move on, okay? And this is another example. Right, so you can see that now there is some potential field. Now you can see that this guy, so this operator manipulate this kind of a virtual fixture to guide swarms down to the obstacles, okay, just like this, that ship holding applications. And also you can see that now, so also operator can use these fingers as well, right? So not only this palm, but using fingers, okay? Then you can see that there are some outlier bad guy or some lost agents, and he can actually nudge by using this hand, okay? And a little bit going more. Right, so goal is, I don't know what is really goal about this operation, but it appears that my students want to make this swarm to split along this cylinder to move from A to B. So that sounds so. That seems so. Okay. So then now you can see that now he can guide this kind of a swarm in 3D environments, just like that we play with the Play-Doh or slime or some virtual water. Okay. Okay, so then it's nice. Okay, so then if we can, so in order to then implement this kind of a system, then prerequisite is we need to track the motion of a finger, right? Right? So then now, in order for you also to try in this direction of the research, I will just overview of a state of art of the hand tracking technology. So this one is Oculus. So this is a commercial product. It's quite nice system. $400, very good system. It has also this inside-out tracking, and you can see that it has this kind of a controller. And if you buy it, then you also would be able to see the fingers as well. Okay, so maybe fingers as well. Okay. However, don't be fooled by this video, because now what you can do is just 1 degree freedom, kind of power grip. Not 1 degree freedom. Right, 1 degree freedom for each finger, open or close, but not this kind of dexterous motion. Okay. Another one is, many of you already have used this system, limb motion, right? Limb motion. Limb motion is based on the camera. Okay. If you have a camera and if you move it, however, I want to make a virtual picture like this, then it will just blows up because it has this kind of occlusion problem, right? Vision-based technology is fundamentally weak in the presence of this kind of occlusion. Okay, and also if you have a limb motion doing this and doing that, then it will just be confused at which one is left and which one is right. Okay. Third way of hand tracking is this kind of IMU. So if you use IMU, then just like a drone, we can actually measure its angle. Okay. So then if we can measure this angle of each skeleton, then we can reconstruct this hand pose. Okay. So then by doing so, we can have this hand tracking. Okay. Then looks quite nice, right? It's a commercial device, right? About $1,000, you can easily buy. Okay. However, it is not really robust in the sense that in order to measure the angle, it uses accelerometer, that's fine. Gyroscope is fine. However, it also needs to use compass, magnetometer. Okay. So then now suppose that you are working on these environments, however, suppose that there is a machine just close to you, or you may hold this kind of a cell phone, hand phone. Then it produces electromagnetic noise. Then hand tracking will be just lost. Then finger will be actually twisted. So not really robust, particularly if we want to take this kind of a human-swarm interaction outdoor or more diverse environments. Okay. And the fourth one is soft sensor. Okay, soft sensor. And you know that it's very interesting. So this stretch sense promotional video is about 2 or 3 months ago. But about 8 months ago, they make a promotional video that you can actually hold some tools, or you can actually punch it. However, tracking can still be preserved. Okay. However, in this new promotional video, they just remove it. Because if you use a soft sensor, okay, then in order to measure its shape, you need to actually measure the deformation of the soft sensor. Okay. However, now suppose that you have this soft sensor, you grip it, okay, grip it, then not only the deformation comes from your motion, but also the contact. Okay, so then now suppose that consider the case that the soldier try to control this drone swarm. Okay, drone swarm. By the way, it's okay to, yeah, let's keep going down. So then in field, okay, so then this commander needs to hold some other device, right? A walkie-talkie, right? So then if he, and also guns, right? Then if hold this kind of a device, so then your tracking will be compromised, because again, soft sensor cannot really distinguish deformation, whether it's from contact or from the motion. So all these technology has that kind of a limitation. So to answer to this this challenge. So we propose this. Okay. Okay. So then, however, in order to really use a human swarm interaction in real world, system should be robust. Okay. So then now in order to attain this robust hand tracking, now we propose this VIST, visual inertial skeletal tracking. But by the way, some of you may say that, so we may use a motion capture system, right? So Vicon, right? If you try to use that motion capture system, you would be easily found that it is not really working well. Because the key issue is that if you have these markers, okay. However, hand tracking is very difficult because space is small, degree freedom is many, and speed is fast. Then if you have this marker, the motion capture system will be confused, particularly due to the problem of data association. Actually, it doesn't know that whether this marker is on this third finger or second finger, because now it's just moving quickly. Very, very complicated. So if you want to use, if you try this motion capture system, you would be able to find that it is not really working well. That's why that there is no very good commercial solution available, which is also robust, even it outside at the moment. Okay. So then in order to solve this problem, we propose this VIST, okay, visual inertial skeletal tracking. And our idea is that we use this marker to use vision information. Okay. However, vision information is weak and fundamentally limiting when there is a occlusion. So then now you can see that it has this glove. Inside this glove, we have this IMU. But IMU, again, if we just use magnetometer, it is not very robust. So in order to make this system robust, we just remove this magnetometer. However, magnetometer provides us north-south information that can be provided by this computer vision problem, computer vision information. So then, now using this, you can see that now this is the Google Media Pipe based on the vision system. You can see that if it's behind of this tablet, it just loses the tracking. Okay, and this is the IMU with this magnetometer. You can see that now it interacts with this tablet. Tablet produces lots of electromagnetic noise. You can see that now finger is twisting. Now this is ours. You can see that it's robust, not only against occlusion, but also against electromagnetic noise as well. Okay. Then now this is one of the example when you use this smart factory that now you can see that so my students is doing this kind of assembly, lots of these ferromagnetic materials, however, still robustly track this hand tracking for all these finger movements as well. Okay. And also that if you just do this in a naive way, not really working, we use a so-called this tightly coupled sensor fusion problem to make it very, very robust. Okay. And you can see that, right? So you can see that the finger tracking is still working when finger is behind of these objects, and also even under the desk, under the table. So it's okay, robust against occlusion. Okay. And also it is working quite well outside as well. So if you use like a machine learning, computer vision, then it is well known that it is very weak with respect to the change of ambient light. Okay, but now it's working inside, working outside. It is very, very robust system, and also some impact. Okay, and also you can see that this guy is opening this ferromagnetic materials. This car door is not still that this is more finger tracking is robustly preserved. And also this is another example for this smart factory. Then now my students is holding this drill. Okay, drill and turn on this drill, and drill has a lot of again electromagnetic noise, right? But it's just working great. Okay, and of course we can also extend it to this dexterous manipulation, right? So then using this finger, not only haptic device just using this fist, right? But now we can use this finger and so on and so forth. Okay. Okay, so then again, we are now in the process of implementing this technology for more realistic and more challenging and more interesting real swarm, 3D swarm interfacing problem. And I wish that maybe next year some of my students can present at IROS. Okay, and we are again in the process. And if we just have this kind of information and this kind of technologies well enough, okay, then perhaps in future we may be able to do this kind of things. Okay, so then multi-users can use their hand to massage this kind of a 3D swarm, drone swarms in this kind of sandbox application for military application as well. And some of them, maybe all of them may be real person, or some of them maybe even, because we all know it's information, because it's AR, right? Augmented reality, we all know, we know all of its information. Okay. Okay, so that's it. And thanks for your attention.
Thank you for your great talk. So we are now open for the questions. If you have any question, please come to the mic or post it on the Slido.
Hi, thank you for the talk. So I'm Maxime from France, NRS. I wanted to know, in your tracking system, the glove is equipped on 3 fingers. So the other 2 fingers, when you have occlusions, are not tracked, right?
Oh, so that is because my students just at the time just have a time to just implement 3 fingers.
Yeah, okay.
Now currently we have this 5 finger with 5 hands.
Okay.
Right.
Okay.
So it's
already done.
Right.
Okay.
Right.
Thank you.
Right.
Are there any other questions? So I have a maybe a bit general question, or maybe it is a bit different.
Okay.
But so when we manipulate by hand, I think the feedback is also important.
Right.
I mean, for example,
right.
We can use haptic feedback
That's
or
correct.
visual feedback.
That's
so you
correct.
talk about the visual feedback, and are there any, how say, ongoing work or haptic feedback?
So here.
Oh, you have haptic feedback.
Right.
on
So
the
we
glove.
have actually 2 ways of providing haptic feedback. First is that we develop, and actually is in this science robotics paper, so that it has this 3D freedom force feedback device about this kind of a size. So we already have that. Then, for example, that if we want to hold objects in this way, then force should be in this way, right?
Yeah,
so then
sure,
it
sure.
needs to provide this 3D freedom haptic feedback. So we have that kind of device. And however, it's a little bit bulky. And I think that in terms of actuator is quite difficult. I mean, not really a good commercial solutions. So another application another direction we are using is a vibrotactile tactile information, and that kind of a vibrator, and then just embed all across this hand. So then maybe that hold it. However, there may be some robots maybe going the other side, then maybe we would be able to perceive it by using this kind of a layer of this tactile actuator. So we are actually doing both of them. And this example is, without this haptic feedback, it's impossible to manipulate this kind of objects.
So thank you. Thank you for the answer. I think very quick question is okay. Yeah.
I wanted your opinion on something. So when you move your fingers, a lot of the muscles right up to the
That's correct.
right up till here get pulled.
That's
So
correct.
there is some technology where they make you wear a band and they use
That's correct.
infrared
Right.
to track the muscles instead of tracking the hand. So I just wanted your opinion on which of this is more effective and why.
Yeah. So actually, you hit the sweet spot, and that's something that is kind of confidential. But I mean that right. So we actually try EMG, not working. not working. But as you said, that the infrared, near infrared, this is something that we will try. Yeah,
Okay.
it should be confidential, but it's disclosed.
Like, are there
Good question.
are there any advantages or disadvantage of both methods?
EMG, I feel that the surface EMG would not work. I mean, maybe my opinion may be too strong, but it seems that the signal to noise ratio is too small. And that's why that we are interested in now exploring the direction of NIR.
Okay.
Right.
Thank you.
Right.
Thank you for the speaker.
Thank you.